In this video, I'll show you how to create your own remote control car using a low-cost RC transmitter and receiver kit that you can easily find in stores. This is the RC transmitter, and here we see the channel 1 control knob, and this is associated with the channel 2. It's like a trigger, and this is on off button, and this is power on indicator, and we also have extra channels with this RC transmitter. And this one is the RC receiver, and it is a PWM type receiver. And you can see channels. Each channels have 3 pins: signal, power, positive and negative. And there are 6 channels. And these are the 3 pins associated with each channel. And you can see the channel 1 here and channel 2 connection here. And this RC receiver operate between 4 to 14 volt DC and operate at 2.4 gigahertz, and this is the antenna of the receiver. And the detector signal pass to the microcontroller, and microcontroller send the signals to the PWM motor controller. First of all, I'm going to show how the signal from the RC transmitter look like using a digital oscilloscope. This is a 2-channel oscilloscope. Channel 1 is connected to the channel 1 of the RC receiver, and channel 2 of the oscilloscope is connected to the channel 2 of the RC receiver. Again, this is the RC transmitter, and this knob is associated with the channel 1, and this trigger is associated with the channel 2. Now, as I adjust the channel 1 on the transmitter, we can observe pulse width associated with the channel 1 is changing on the oscilloscope. However, the change is very subtle. Therefore, I'm going to increase the resolution of the oscilloscope in order to observe the change clearly. Now, when I change the knob, for instance, if I rotate the channel 1 knob in clockwise direction, you can see the width of the pulse increasing. And also when I rotate the knob in opposite direction or anti-clockwise direction, the width of the pulse decreasing. So this way we can change the pulse width of the channel 1, and similarly when we change the trigger of the RC transmitter, we should be able to see some changes on the channel 2 of the oscilloscope, and it is the blue trace. You can see when the trigger is pulled. Let's learn the fundamental of pulse width modulation or PWM concept. A PWM signal is essentially a series of fixed frequency pulse train with variable pulse width. In our RC signal, the frequency of the pulse train is 50 Hz. This gives 20,000 microsecond signal period. The signal is switched between high and low logic state. The control information is then encoded in the duration or width of the pulse. The duty cycle in a PWM signal indicates the proportion of time the signal is in the on state relative to the entire cycle duration, typically expressed as a percentage. A higher duty cycle signifies a longer duration on time compared to the off state. Now let's consider the PWM signal of the RC channel 1. When the knob is at its midpoint, the pulse width is around 1483 microsecond. When the knob is at maximum position, the pulse width extends to 1770 microsecond. While at the minimum position, it goes to 1194 microsecond. This can be translated into duty ratio of 7.4, 8.8 and 5.9 respectively. Duty ratio of the channel 1 remains within a narrow range, especially varying from 5.9 to 8.8. Now let's consider DC motor control basics. By altering the average voltage across the terminal, we can control the speed of DC motors. This can be achieved by switching these power electronic switches or transistors. This type of circuit arrangement is called edge bridge driver circuit. The on duration of these switches is dictated by the width of the PWM signal. By varying the duty ratio of the PWM signal, we can vary the average voltage across the motor. For instance, in this case, average voltage across the motor is 3.6 volt. When the pulse width increases to 80% duty ratio, then the motor speed also increase. If we want to change the motor's direction, we need to maintain these two transistors in off position and apply PWM signal to other two transistors like this. The LN298N motor driver board is a popular dual edge bridge type motor driver module widely used in electronic projects. The boards consist of two edge bridges, allowing it to control two DC motors independently. Each edge bridge can drive a motor in both directions. We can apply PWM pulses to ENA and ENB pin. Then direction control pin IN1 to IN4 determine the rotational direction of the two motors. Output 1 to output 4 facilitate the connection of two DC motors. In this scenario, both motors are set to rotate in clockwise direction with duty ratio of approximately 20%. Direction of rotation is determined by the logic applied to the IN1 to IN4 pins. In this case, both motors are rotating at same speed as the same PWM signal is applied for both ENA and ENB pins. As the duty ratio is elevated, the motor accelerates. However, it continues to rotate in clockwise direction since the control bits remains unchanged. When the direction control bits are changed, the motors rotate in anti-clockwise direction. In this scenario, two motors rotate in opposite direction at different speeds. Let's investigate the difference between the two PWM signals discussed earlier. The PWM signal from the RC system operate at a frequency of 50 Hz and have relatively narrow duty range spanning from 5.9 to 8.8. Conversely, when it comes to regulating a DC motor, a broader duty range is necessary, typically ranging from 20 to 100. Therefore, we can't directly apply the PWM signal of RC receiver to control a DC motor. To address this, we specifically need to map the narrow duty range of the RC signal onto a wider duty range suitable for controlling a DC motor. In the next few minutes, we will demonstrate the process of implementing this mapping, illustrating how a simple controller can be designed using ESP32 microcontroller. Here is the comprehensive circuit layout of the control system. This comprising an RC receiver, ESP32 microcontroller and a to 98 in motor driver circuit. Additionally, logic level shifters are incorporated since the motor controller and the RC receiver function at 5 volt while the ESP32 operate at 3.3 volt. The motor controller effectively translates this RC signal into a PWM control signal governing the direction, speed and steering of a toy car. Also, we need to have variety of control features to steer a toy car. In coming section, we are going to show how such a controller can be developed using low-cost ESP32 microcontroller.
Hello everyone! In this video we'll dive into the code for an ESP32 based project design to determine the pulse width modulation or PWM signals from a 2-channel RC receiver. These signals can be used for various applications like controlling motors and robotics. Let's understand how this code works. Firstly, we have the necessary includes and declarations. The code uses interrupts, tasks, and semaphores for efficient multitasking on the ESP32. Two PWM signals from the RC receiver are connected to pins 34 and 35, and we've defined the corresponding interrupt pins. We have interrupt service routes for both rising and falling edges of each PWM signal. These handlers record the time of the rising and falling edges, allowing us to calculate the pulse width of the signal. The handle rising edge 1 function is an interrupt service route or ISR designed to handle the rising edge of the channel 1. It records the starting time of the pulse and sets a flag to indicate that the first pulse is in progress. Similarly, the handle falling edge 1 function handle the falling edges of the channel 1 signal. When a falling edge is detected, it records the ending time of the pulse and resets the flag, indicating that the first pulse has ended. These two functions allow us to precisely measure the duration of the pulse width of the channel 1. The channel detection process has predefined maximum waiting time of 30 milliseconds, determined by the interval variable. If a pulse is not detected within this time frame, the system initiates the detection process of channel 2. In this code, a multitasking approach is employed through the utilization of two tasks, namely task 1 and task 2. We've created a task named task 1 RC signal reading. This task continuously reads the PWM signals from the RC receiver using interrupts. It calls handle rising edge and handle falling edge subroutes to capture the pulse widths of the two channels and then updates shared variables with the semaphore for safe multitasking. Task 2, named Task 2 Motor Control, retrieves the pulse width values from the shared variables and prints them to the serial monitor in the first example. We are going to extend Task 2 to control the speed of motors in our next example. In the setup function, we initialize the necessary pins, set up PWM configurations, and create tasks and semaphores. We also configure the built-in LED for visual feedback. The loop function is left empty, and the task handle is continuous operation of the program. Incorporating multitasking into this code brings about significant advantages, enhancing the overall efficiency and reliability of the system. Let's explore the key benefits of the multitasking approach employed here. Task 1 is dedicated to the crucial task of accurately measuring the pulse widths of the received signals from the RC receiver. This is a time-sensitive process where detecting the rising and falling edges with precision is paramount for determining the pulse width of each channel. On the other hand, Task 2 takes the responsibility of utilizing these pulse width values whenever necessary, specifically for controlling the motor of the car. By segregating the functionality into a separate task, we achieve independence in the motor control process. The true advantage lies in the isolation of these processes. Task 2, being independent, does not interfere with the time-critical signal detection process performed by Task 1. This ensures that the accuracy of the pulse width measurement is maintained, unaffected by the operation in Task 2. Let's proceed to upload the code to ESP32 and observe how it reads the pulse widths of channel 1 and 2. Using Arduino IDE, we can upload the code using the upload option in the menu. Also, in the ESP32 Wardroom DA module, the boot button on the board needs to be pushed to initiate the upload process. Utilizing the serial monitor in the Arduino IDE, we can monitor the values. The code includes print statements to display the readings. When the control wheel for channel 1 and the control trigger for channel 2 are in their rest positions, we obtain a channel 1 pulse width of 1482 microseconds and channel 2 pulse width of 1473 microseconds. As the channel 1 wheel rotates clockwise to its maximum position, the pulse width reaches 1770 microseconds as the maximum. Conversely, when rotated counterclockwise towards the end, the minimum value is 1194 microseconds. Similarly, for channel 2, the maximum and minimum values are 1481 microseconds and 1465 microseconds respectively. In this extended version of Task 2 code, we broadened the functionality to control the movement of a toy car with 2 motors. Let's break down the process step by step. The initial step involves determining the maximum, minimum, and mid values for both channels. The mid value for a channel is obtained when the corresponding control, such as the wheel of the RC transmitter, is in a rest position. Users can rotate the control clockwise or anti-clockwise until it reaches the maximum or minimum limits. These limits and the mid value for both channels are initially determined using the code explained in the previous example and hard-coded into this code. However, the next example will show how the code can be further extended to automatically calibrate these values when the car is turned on. For now, we are using the hard-coded values for simplicity. The modified Task 2 function compresses an infinite loop that continuously captures the pulse widths of channel 1 and 2 using getPulseWidths function. The pulse width of channel 2 is then mapped into the PWM duty cycle variable, controlling the car's movement based on trigger actions. When the trigger or channel 2 is pulled, the car moves forward, with the speed determined by the trigger position. When the trigger is at rest or in the middle, the car stops moving. When the trigger is pushed, the car moves in reverse. The speed is once again determined by the trigger position. Channel 1, associated with the wheel of the RC transmitter, is utilized to change the relative speed between the two wheels of the car. Rotating the wheel clockwise results in a position duty cycle delt value, while anti-clockwise rotation yields a negative value. When the wheel is at rest, duty cycle delt is 0. The overall pulse width fed into the right side motor is calculated as duty cycle minus duty cycle delt. Similarly, the pulse width fed into the left side motor is calculated as duty cycle plus duty cycle delt. In this manner, the car's direction can be controlled using the wheel or channel 1 of the RC transmitter. The code dynamically adjusts the motor speeds based on the trigger and wheel positions, allowing a versatile and responsive car movements. In the third iteration of the Task 2 code, significant enhancements were introduced to enable the automatic calibration of the maximum limits of channel 1 and channel 2 when the car is powered on. The process involves acquiring the neutral values of channel 1 and 2 signals initially. To initiate the calibration, the user sequentially rotates channels their maximum and minimum positions. At the end of each step, the code prompts the user by blinking an LED, signifying the transition to the next calibration phase. The calibration steps are as follows. Turn on the car. Wait until the LED blinks to calibrate the mid positions of channel 1 and 2. Rotate channel 1 to its maximum position or clockwise and wait until the LED blinks. This action calibrates the maximum positions of channel 1. Rotate channel 1 to its minimum positions or anti-clockwise and wait until the LED blinks. This step calibrates the minimum positions of channel 1. Pull the trigger of channel 2 and wait until the LED blinks. This process calibrates the maximum positions of channel 2. Push the trigger on channel 2 and wait until the LED blinks. This step calibrates the minimum positions of channel 2. The potential of this code extends beyond calibration. It can be further refined to incorporate protective functions, automatically halting the car if it moves beyond the signal range of the RC transmitter.